Edge. No, I'm zoom. In edge here. Aquí ya está bajado. So. Where you want.
Good afternoon. Thanks for coming today. Dario Sciandra, right? We present today. He's a third year PhD student from at the GeoRest group. And here at Imedea, the group is part of the climate change group. And he is going to talk today about geological carbon storage. Dario, the floor is yours.
Thank you. So today, you already said that I'm on the third year of my PhD under the supervision of Dario Sciandra, is here, and Imedea, he is not here, unfortunately. So I'm going to talk about basically the first task of my PhD, which referred to the numerical modeling of this material that we call Opalinus Clay, which is a caprock-like material during the injection of CO2. So to introduce the problem, we already know that there is a connection between climate change and CO2 emissions. And from COP26 in Glasgow until now, I think this weekend it starts the COP27 in Egypt. But we already know that we didn't feel the expected reducing emissions of CO2. Actually, by 2030, we are planning that, like globally, it is planned to increase the emissions of CO2 by around 11%, while for the Intergovernmental Panel on Climate Change, we should reduce the emission by 45% on the same, until the same period, so for until 2030 to reach this goal of keeping the global warming under 1.5 degrees. So to see it more the plots on the left side, here there is the anthropogenic CO2 emissions over the last, in gigaton scale, over the last 30 years. As you may notice, the tendency is to growing into the emissions, not lowering. Even after COVID pandemic, there is a tendency, it restarted to grow instead of lowering. From the IPCC, on the other hand, on the right plot, what I put here are the pathways to limit the global warming predicted by the IPCC. And as you may notice, all the pathways, they consider that around 2050 we reach negative emissions, and after that we even have negative emissions. So IPCC gives, apart from giving these pathways, gives an hint on some actions that we can make and some technologies that we have to introduce to do this, to reduce of 1.4 billion tons of CO2 per year, reach this zero value by 2050. And between those technologies that they consider to implement, there is what we call the geological carbon storage. So for geological carbon storage, what we mean is to after collecting CO2 from different sources, like directly from the air or from industrial facilities or from biomass energy, to inject it at a certain depth. This depth we refer to depth higher than 800 meters, and I will explain you why using with the help of this figure, which represents the density variation of CO2. We refer to the depth. As you may know, going deeper into the Earth, we have a gradient of temperature and pressure. The temperature and pressure grows. This means that the CO2, the change is density with that. So if we inject the CO2, like 1 cubic meter of CO2 in the depth of, for example, 400 meters, this same amount of CO2 has a volume of 80% reduced volume if we inject it at 800 meters. So that's why basically we improve our storage. The same amount of CO2, we need much less space to do that. The other advantage to go deeper is given by the fact that the path that CO2 needs to return into the atmosphere, which is a problem, of course, is longer. Deep we go, the longer it is. After this value, we reach more or less the critical state of CO2. So CO2 is not anymore gaseous in gaseous phase, but is in the supercritical state. So this gain that we had at the beginning, we don't have it anymore. So we limit more or less the range of that for this technology, usually conventionally between 800 meters and 1.5, 1.6 kilometers because of this. The formation we would like to inject CO2, we call it the reservoir formation. It is a rock, of course. So we should consider that as a both solid part, but also with some voids filled by fluid part, you know? So it already has a fluid. But in this case, we refer to usually as brine. So when we inject CO2, the CO2 tends to spread laterally for kilometers, but not only spread laterally, but since the the brine that is already in the reservoir has a higher density than the CO2, CO2 tends to go upward. And at a certain point, it will reach the interface of the upper formation that we usually refer to cap rock. So if the reservoir is a formation that has a characteristic that allows us to inject it, so it has, let's say, a good porosity and a proper permeability to let the fluid flow, the cap rock at the opposite has and we would like to have it not a high porosity, a low porosity and a low permeability, and also a high entry pressure. So CO2, when it reaches this interface, to be able to enter really in the formation needs a lot of pressure. So one of the problems then one of the questions of geological campus storage, not the only one, but one of the main ones that I would like you to focus on at the moment is the leakage problem. So the possibility of the CO2 to pass through this cap rock and return into the atmosphere. That of course is a problem. During the last decades, it has been globally, mainly in the US and Europe, a growing interest on this kind of technologies, as you may notice from this map. And since the interest is growing, we would like to develop more specific characterization processes for this technology. So in particular, here on the right side, what I draw is the steps predicted by the European Directive for geological thermal storage. So what you usually have, for example, if you see here, depleted gas, depleted oil, you have, or together with other technologies, you have sites at which you already have done something. So you already have some information about the site that you have. It is very important then to collect all the data that you have historically, fill the gap that you have, then generate your model to give an infant risk assessment, which is connected. One of the risk assessment, of course, is the leakage that we were talking before. And when you start the operation, you should plan your monitoring paths. And with the monitoring path, you collect new data to be able to update your models. But with that, what you lose is the fact that the characterization process is also a multi-scale process. So what you usually starts is you start with having some sample of the different information that you have. You try to test them. The good thing about this is that you impose your boundary conditions. So you define the properties of your material with a very good precision, because you know what you're doing, because you're imposing it. But at the same time, the disadvantage of this is the fact that you have a time and space scales which are different from what we are really interested in. So the in situ values. The problem with the in situ is the fact that we do not really control everything there. So we have certain unknowns and then uncertainties on that. So the idea introduce what I would like to talk to you about is the idea is for filling the gap between these two scales, to put something in between, which is the underground rock laboratory characterization, which is a situation in which you have a tunneling system in which you directly have access to the rock formation. In situ, you don't access the formation. In here, yes, you have a gallery system, you access the formation. You can drill your wells. Here, you have a kind of very refined monitoring. So you have a very good control of what is happening. And you're able to discard at a scale which is still not the in situ scale, but it's something nearer compared to this one. So we will focus now on the underground rock laboratory, and in particular to this underground rock laboratory, the Monterrey one, which is located in the northwest of Switzerland. Here I reported the planar view of the rock laboratory. You may see here this is a motorway tunnel that passes through the Jura mountain system, and this is the security gallery of the motorway tunnel. So since the 90s, they started here to build some experience. In reality, the principal aim at the time was the nuclear waste disposal. And then after they start to drill more tunneling system just dedicated to explore this formation, which is Opalinus Clay, all of this, divided in three different patches. Then the last extension, which is this one in V, ended in 2018. In this last extension here in the CL niche, it is the place where it's supposed to be this CO2 long-term periodic injection experiment, or cool pipe. From this, what we have is the photo of the installation front. So while they were drilling, at a certain point they stopped around here and they took a picture. And from this, what you can see basically is this large-scale anisotropic, these bedding planes, we call them, inclined more or less at 45 degrees with respect to the horizontal. So we sketched the planned experiment there. So the idea is to drill a well of 10 meters by 10 meters, because when you drill a tunnel, you are disturbing the rock around it. So you have, in the case of Opalinus Clay, you have around 10 meters of disturbed zone. So you want to reach the undisturbed zone by this 10 meters, and then you inject just in the last 20 centimeters there. When you inject, in general, doesn't matter if it's this cool pie experiment or in general in a reservoir case. What happens is that you have a different hydrothermal, mechanical, and chemical coupled effects that happens at the same time and then influence each other. So, for example, if we think about the first case, the reservoir, what we do is we impose a pore pressure with a certain pore pressure to be able to inject the fluid inside the formation. But the fluid that we inject usually has a lower temperature than the one of the rock at those depths. So it means that there is a gradient of temperature that you're imposing. At the same time, the CO2, you're injecting a fluid which is different from the one that you have there. So it will interact chemically, not only with the fluid, but as well with the rock. And all of those will change the stress field and as well the deformation. They will tend to expand, for example, the rock around the well. So all those effects happens at the same time and influence each other. In the case of cool pie, in our case, what we need is to limit the analysis to the hydromechanical. So what we do is we impose a certain overpressure, then we get some expansion around the injection, and this in turn changes the void inside, so it changes the porosity basically of the material. To return to actually I have some samples here of those two rocks. This is taken from Bagna Buffar, and this is taken from Monterrey. So I can Monterrey one if you want. The thing that I was saying before, I gave a hint on the fact that we had these bedding planes before. I want to comment more on that by saying that, for example, if you see this one that is taken from Bagna Buffar, you clearly see by the way that it has been broken, the fact that you have two directions here that define two perpendicular directions that define a plane at which you have more or less the same properties. Then you have another direction, which is this one, perpendicular to this plane, which has different material properties. That's what we analyzed as well, what we see as well, what they saw as well in the laboratory for Opalinus Clay. So they define different values, normal and perpendicular and parallel to the bedding planes. And we decided to use them with a mathematical model, an isotropic model, which is called transverse isotropic model, to take into account this anisotropy that this material has. So we define our domain as a 20 meter per 20 meter here, finding an homogeneous but non-isotropic material. So in this material, we already said about the hydromechanical properties of the material. We had to impose the initial condition that are here for both for the hydraulic part and for the stresses, the mechanical part. To be able, in particular, we imposed a linear gradient for all the four quantities: the liquid pressure, the vertical stress, and the two horizontal stresses. Three. So we complete all of that in order to have a lithostatic and hydrostatic pressure. So as we said before, undisturbed condition before the injection. Then we impose the boundary condition. In particular, here we don't have displacement, vertical displacement on the bottom side, and here we don't have lateral displacement on the lateral sides, and we impose at the top a constant stress, which is coherent with this value here. Then what we do is at the injection well, we impose an overpressure. We impose this variation of the gaseous CO2 pressure inside the well that propagates around in the formation with a mean pressure of 3 MPa, with an amplitude of 0.5 MPa, and with a periodicity of 1.75 days, more or less. We impose this for 20 years, and what we get is represented here in terms of, this represents some way the hydraulic part, and this represents more the mechanical. This in particular is the liquid pressure around the well. This is the well. As you may notice, it's influenced by the bedding direction, as we said. Okay, so the overpressure goes more on the bedding direction. And this one, this is the effective, we call it effective mean stresses. So if you take the three components that I said before, the vertical and the two horizontal, you make an average. Then you take out the fluid pressure and you get this value. Basically, it represents the stresses, the effective stresses. And they are at the same, also influenced by the plates. So both the hydraulic and the mechanical part are influenced by those. Finally, what I wanted to show you was, we said about the leakage problem before. So now we assess, so what is the flow of the CO2 inside this formation of Opalinus Clay? It is supposed to be like a caprock, no? What happens is that, if you remember, I said at the initial, the liquid pressure was the hydrostatic one, and this at the level of injection was 2 MPa. Then we impose an average of overpressure of 3 MPa. So we have a difference of 1 MPa imposed at the injection level. This is lower than the pressure that the CO2 needs to enter as a free phase inside the formation. So the CO2, the gaseous CO2 that we are injecting doesn't enter as a CO2, as a gaseous phase inside the formation. It dissolves inside the liquid that you have on the formation. It dissolves inside of it. Okay? So it flows by the fact that there is a difference in this liquid, there is a difference of concentration. So it spreads because of this inside the formation, reaching around 2 meters after 20 years. You may ask why it's not following this. It's just because this flow is dominated by the molecular. This difference of concentration of the molecular diffusion is not influenced a lot by the advection of the liquid part. So finally, what we could say is that we helped the design of this experiment that hopefully next year will start. And we gave them some hint about the stability of the material, about the flow of CO2, and then some hint about how to put the monitoring devices to be able to, of course, we like the fact that it behaves like a caprock, but at the same time, the flow it means that it's very slow. So we gave them some numbers to tell where to put the monitoring devices to be able to measure something even in the first month of the experiment. You know? This work that I presented is in more detail reported here in some of our publications, this publication in particular, which is in Geomechanical and Geophysics for Geoenergy and Georesources. If you want that, you can ask me and I can give it to you. And that's it basically. If you have any questions, I have some other results as well if you want to see them. Thank you. If you have any questions.